Imagine looking into space and seeing what appears to be a little smudge. But hold on, that smudge is a big deal. It's not just any smudge, it's like a peek into the past, all the way back to the beginning of time. And guess what's hiding within that smudge? A massive galaxy with an even more massive black hole at its center. This black hole is so far away, it's almost at the edge of what we can see. But here's the kicker. It might just hold the key to one of the universe's biggest mysteries, where those supermassive black holes come from. Cool, right? Let me introduce you to Abell 2744, a colossal gathering of galaxies about 4 billion light-years away, which is pretty much next door in cosmic terms. Now, what's really intriguing about this place isn't just the galaxies themselves, but what lies beyond them. Imagine a vast halo of dark matter stretching across a whopping 4 million light-years. This dark matter bends and distorts space, acting like a gigantic magnifying glass for light passing through. That's why Abell 2744 acts like a cosmic lens, helping us see much farther than we could with our regular telescopes. It's no wonder both the Hubble and James Webb Space Telescopes couldn't resist taking a closer look. Now, here's where things get exciting. The James Webb Space Telescope, or JWST, has this amazing ability to see in the infrared spectrum. When it trained its eyes on our smudge, it revealed something mind-blowing. The light coming from it had been stretched out by the expanding universe, turning it into infrared light. This stretching, called redshifting, tells us a lot. A redshift factor of over 10 means this light has been traveling for an astonishing 13.2 billion years, almost since the dawn of time itself, when the universe was just a tiny fraction of its current age. That's why we've dubbed our smudge UHZ1, short for Ultra-High Redshift Galaxy number 1. And that Z, well, it's the symbol for redshift, marking this as an extraordinary find. All right, so JWST has spotted galaxies even farther away than our smudge, but the real jaw-dropping moment happened when we aimed another space gadget at it. Behold, the image from the Chandra X-ray telescope. Turns out, this little blob is a powerhouse of X-rays. Now, X-rays are tricky to focus, so those 4 pixels of light aren't scattered randomly. They're coming from somewhere within this blob. And guess what's known for emitting X-rays like this? Yep, you guessed it. A quasar. Now let me jog your memory about quasars. Picture this. At the heart of every galaxy lies a supermassive black hole. When these black holes start munching on matter, they turn into quasars. The feeding frenzy heats up the surrounding material so much that it shines brighter than the entire galaxy. And right before the matter plunges into the black hole, it releases a burst of high-energy X-rays. Based on the amount of X-ray light and how far it's traveled, we figure the black hole in our smudge must be a whopping 40 million times heavier than the Sun. That's like 10 Milky Way-sized black holes put together. UHZ1 isn't just any quasar, it's the farthest one we've ever found, making it the earliest known quasar and giving us a peek at the universe's earliest black holes. Now let's dive into the juicy stuff. To grasp why UHZ1 has us all buzzing, you need to wrap your head around one of the biggest debates in cosmology, the origin of supermassive black holes. Here's the deal. Nearly every galaxy out there hosts a black hole at its core, ranging from 100,000 to several billion times the mass of the Sun. We've also spotted smaller ones called stellar black holes, weighing in at around 10 to 100 times the Sun's mass. But here's the twist. We're missing a bunch in the middle, the ones between 100 and 100,000 solar masses. It's puzzling, right? We know how stellar black holes form. When a massive star bites the dust, its core collapses in on itself. But how do you make supermassive black holes bulk up? That's the million-dollar question. One theory is they chowed down on gas and merged with other black holes over billions of years, starting from the universe's infancy. But here's the kicker. We've stumbled upon quasars shining from the first billion years of cosmic history, powered by black holes that shouldn't have had enough time to grow so massive. Now let's tackle this puzzle with two potential answers. First up, we've got the small seed model. Picture this: tiny black holes starting out and somehow bulking up super fast. But here's the catch. Can a run-of-the-mill dead star morph into a quasar engine in less than 1 billion years? It's a tough call. You see, black holes have a limit to how much they can gulp down, even if there's a never-ending buffet of gas. As the gas swirls in, it gets heated up and shoots out radiation, kind of like a cosmic pressure cooker. The bigger the black hole, the more it can eat and radiate, but there's always a cap on how much it can handle, called the Eddington limit. Crunch the numbers and it turns out these small seed black holes just can't grow big enough, fast enough to explain those early quasars. Sure, there are some nifty tricks we can pull to make the math fit, like speeding up the feeding process or having lots of black holes merge in a hurry. Or maybe those early stars were giants, leaving behind monster black holes hundreds or even thousands of times bigger than the ones we see today. But even with these tricks, there's still a missing piece in the puzzle. Why no black holes in the middle range of 100 to 100,000 solar masses? If supermassive black holes evolved from smaller ones, shouldn't we spot some leftovers in that range? But nope, they're nowhere to be found. All right, let's flip the script and explore the heavy seed model. What if supermassive black holes didn't start as hyperdense cores of dead stars? Fun fact, you don't actually need ultra-dense stuff to create a black hole. For any given amount of mass, there's a critical size it needs to be squished into to form a black hole. That's the Schwarzschild radius. Take the Sun, for example. If you squeezed its mass into a space about 3 kilometers wide, you'd have a black hole. Now picture a behemoth black hole 1 billion times the Sun's mass. Its Schwarzschild radius would be as huge as Neptune's orbit. That's like stuffing 1 billion suns into an area with the density of cotton candy. Crazy, right? While the early universe wasn't exactly overflowing with cotton candy, it was brimming with gas that would eventually birth stars and galaxies. Did you know that in the early universe, some gas patches collapsed straight into black holes without forming stars? That's right. These direct collapse black holes match that elusive middle range we've been puzzling over. It's like skipping the line at a cosmic buffet and jumping straight to the good stuff. So what's next? Well, buckle up, because there's a whole universe of discoveries waiting for us. From unraveling the origins of supermassive black holes to exploring the birth of galaxies, we're just getting started. Hit that subscribe button and join our community of space explorers.